Okay, so Newton's third law of motion, short name, action, reaction. You probably have heard it called this. For every action, comma, there is a reaction. How many of you have ever heard that before? Okay? That is a crappy definition. All right? It leaves out so much and is so vague that you just apply that to anything. When I hear someone say reaction, I'm thinking my mom getting mad at me because of something I said or something I did. Okay? Reaction, action. We're not talking about emotions. All right? We're talking action and reaction. We're talking about forces. Okay? Both of those are discussing a force. So, a good definition, okay, that actually makes sense. Here we go. When one object exerts a force on another object, the second object exerts an equal and opposite force on the first object. Now, obviously that definition sounds very blah, 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 blah. Okay? That's why they say action, for every action there's a reaction. Okay? But this definition is far more complete and less ambiguous. Okay, but the key words in this are equal and opposite. Okay? We're talking about forces that are being equal and opposite. So, what does it mean to have equal forces? Final piece of paper says equal forces. What does it mean? As little glue as possible on that. It says equal forces, both forces have the same magnitude. Okay, when we're talking about force, we're talking about magnitude. What on earth are we talking about? The magnitude of a force. The forces have equal magnitude. What is that talking about? What does that mean? What does it mean?
Equal magnitude?
Mm-hmm.
Kind of like the same weight? Or no, not really.
We're talking about force, so...
Mass.
No, force and mass are different variables. Alright? Equal forces, we're talking about, yes, strength. Magnitude, we're talking about the strength of the force. How strong that force is. Okay? So equal forces, both forces have the same magnitude or the same strength. Okay? Now, what's the unit of measure for force? If you don't remember, go back to your notes on page 23. Notes on page 23. What are the units for force? So page 23, force measured in newtons. Okay, so we're talking about the same newtons. Okay, we're talking about the same strength. Now, these two forces in Newton's third law are both equal and opposite. So, what does it mean to be opposite? Go ahead and glue that in. Opposite forces. The forces are moving in opposite directions. Because remember, force is a vector. Okay? Remember, force is a vector. That means force has both size and direction. Fancy word for size is magnitude. Okay? Force is a vector. It has magnitude and direction. So the magnitude of these two forces is the same, but their directions are opposite. All right, so let's get a visual example. What are we talking about? Below here, I want you to draw a nice big arrow. Now, I want you to draw the mirror image of that arrow. I want it to be the same length, but I want it pointing the opposite direction. Okay, make sure those two arrows are the same length, but pointing opposite directions. Okay? We see here opposite direction. Okay? Let's go ahead and label. This one's 10 newtons and that one's 10 newtons. Okay? A 20 newton one would be twice as long. All right? They have this equal strength. Okay? So these are equal and opposite forces. Okay? We get it? Make sense? Okay. Now, we are going to talk about, in a few days, net force. Okay? And net force is often confused with Newton's third law. So, whenever you're trying to figure out if you're discussing Newton's third law or some other law or what's going on, always make sure that you're talking about two different objects. In order to be discussing Newton's third law, there must be two objects. Okay? Go ahead and highlight that. There must be two objects. In order to be discussing Newton's third law, we're talking about two different objects. So, let's go through some classic examples. Okay? So, some classic examples. We've got the hammer and nail. Okay? That hammer hits that nail with 5 newtons of force. And every time that hammer hits that nail with 5 newtons of force, the nail hits the hammer right back with 5 newtons of force. Okay? Now picture, okay, how many of you have ever hammered a nail? Okay? Hopefully everybody. If not, that's a life experience you ought to have. Okay? So imagine yourself holding a hammer and going through that motion of hammering a nail. Okay? And actually like hammering a nail. Now imagine what it would feel like after doing that for 30 minutes. Hammering nails for 30 minutes. What's your arm going to feel like?
No.
Yeah, numb. It's going to hurt. It's going to be tired. It's going to be sore. Okay? Now imagine yourself doing the exact same motion, but just moving your arm without actually hitting a nail. Is it going to hurt as much?
No.
No, it's not. Okay? The reason why is because of this right here. You're doing this, but then your muscles have to deal with getting hit by 5 newtons every time. You may put 5 newtons of force into that nail, but the nail puts 5 newtons of force right back into your hand, into your arms. Okay, because it hits the hammer, and your arms and your hand have to deal with that. And so every single time, you're actually doing a double hit. You're putting in 5 newtons, and you're getting 5 newtons back. All right? So that's what's so exhausting about hammering a nail. Okay? Does that kind of make sense? All right. Next example. The two people pushing off each other. Go ahead and glue that in to the right. Now look carefully at those two people. What do you notice? Careful observation. What's so particular about things? Yeah, they're not wearing tennis shoes. They're wearing ice skates. They're on skates. What does that imply?
Less friction.
All right. Skates, we're implying less or no friction. Okay? When we've got skates, we're dealing with less friction. So when these two push off of each other, you're actually going to see them move. Okay? Making sense? Yes, yes? All right. We're actually going to see them move. So here's the interesting part that's kind of hard to believe, but it doesn't matter how strong one person or the other person is. Whatever force is pushed off with, they're both going to be pushed against each other with the same force. So, for example, I put here 40 newtons. It's going to be 40 newtons of force on both people. Okay? Does that make sense? So it doesn't matter if this person over here is super strong and this person's super weak, or vice versa. This person's super strong. She looks a little more athletic. All right? This looks more like a grandma. So the athlete and the grandma, and they push off each other. Obviously, this person's much stronger, but it doesn't matter. It's still going to be an equal force that pushes them both off against each other. Okay? Now, just like in the picture, hand to hand, push off against each other. Here, let's get you guys closer. That'll be a little bit easier. Okay? Push. Now, push like, push. Oh. Like, I want you guys like, okay, they both move away from each other. Yes, we expect that, yes? Yes. All right? Now, back together. Turn around for me. Okay? Now, you're just going to push a little closer. Okay? Now, feet up. Just push off of the chair. Push off his chair. Yep, you're just pushing off. Again, they both moved. Now, wait a second. The chair, it wasn't thinking, I'm going to push against Sky, right?
No.
No, the chair doesn't think. But yet, Sky moved that direction. Yes?
Mm-hmm.
So obviously there was a force pushing him that direction. You guys see that? So obviously there's a force involved. Thank you, gentlemen. Go sit down. I need another volunteer.
Do I stop?
Someone really, really small. All right. Now, those two gentlemen were of similar mass. Now we're going to do very different mass. Okay? All right? Ready? Push. Now, what was the difference in that motion?
She flew.
She flew! Okay? Now, am I super strong? No. It goes back to Newton's second law. She's got the less mass, same force, she's going to accelerate more. Does that make sense? I accelerated a lot less because I got more mass. But it was the same force. Okay? So, sit down. Now, turn around. Now, again, I'm going to push her, okay? But now, it's only going to be my strength. So, she doesn't go as far, neither do I, but she still goes farther. Does that make sense? She still accelerates more, but because there's less force going on, same force, just less force, she accelerates less, but I also accelerate less. Okay? So does this make sense?
Yes.
All right. Thank you very much.